First one is going to be given by Martin Plavala. So can you maybe stop sharing, Jonathan, if you can?
Mm-hmm.
Great. So Martin, please.
Yes, hi.
Hello.
So you should see my screen now.
Yeah, there is some black. Wait. It's getting there. Okay, there were some black rectangles, but you're moving them out, right?
Yes, yes, yes.
Okay. So please.
Yeah, thank you. So I guess welcome everyone to the talk. What I'm going to tell you something about is about how to do operational theories in phase space. So this is this was done in collaboration with Matthias Kleinman from the University of Siegen. And so this is the main idea. In classical and quantum theory, we have these two aspects. The first one is the finite dimensional information theory, and the second one is the physical theory, position, momentum, energy, and Hamiltonians. And these are usually somehow treated either as separate aspects or they somehow talk only very little. And well, then there's the GPTs. And so we already heard yesterday and today something about GPTs, but the main idea here is that GPTs are theories which go beyond classical and beyond quantum. So there are theories which, they're a big class of theories that includes both classical and quantum theory. And so in GPTs, one usually only investigates these finite dimensional information theories with black boxes and Bell inequalities. And what we did, what's the main task, what's the big project, is to formulate harmonic oscillator in GPTs. And so this is what I'm going to tell you and show you how to do. So, so why should you care? Like if you're a GPT person, you're probably at least a little bit interested. If you're not a GPT person, well, it's quite interesting because it gives some alternative to quantization and also gives some insight into what actually happens during quantization. And also I would argue that looking at this, at quantum theory from outside, looking at it from the perspective of GPTs gives us better understanding of quantum theory. So this is the big idea. So let me first start by somehow intuitively introducing the GPTs. Although we've already heard this twice or thrice, I guess it's good to repeat it for those people that maybe missed or don't remember the other talks. So the big idea is as follows. Here on the left, we have the Bloch sphere. And we know that the Bloch sphere contains quantum states. And the idea is, the main idea is quite simple. So what if we would replace the sphere by a cube? Well, two things happen. First of all, even for a cube, we can formulate many things in a very similar way as we can for a Bloch sphere. If we just restrict to the convex structure of the Bloch sphere, the cube is not that much different. It's also 3D, and we can formulate many things that we know in quantum information theory also if the state space would be a cube. But an important thing happens, and that is that if the state space would be a cube, there would be no Hilbert space. So, and this is very important to remember going on, that in GPTs, there is no Hilbert space. By going away from quantum theory, we also go away from Hilbert spaces. And so we don't have Hilbert spaces in GPTs. And in general, we don't even want to have them because as soon as you assume that you have a Hilbert space, well, I mean, then you have a quantum theory and you don't have a general theory, and we want to have a general theory, so no Hilbert space. So then, as we already saw before and also today, this is the main structure of every theory. We have a state space K, and then we have, which is a basis of some cone, and this somehow gives enough structure to formulate a relatively meaningful information theory of some finite dimensional objects. So then again, if you know GPTs, or if you remember the previous talks, you already seen this. If not, then I guess you get to see this strange ice cream cone once again. And so this is the structure of the finite dimensional theories. But now we want to do this in phase space. So we want to do something infinite dimensional. And so it's going to be a little bit different. So what we need to do in infinite dimensions is this. We need to assume that there are some position and momentum, which are real numbers, and we are going to have only one position and one momentum. And we will assume that states of a theory are going to be given by pseudo-probability densities, which means that these are functions or in general distributions, which don't have to be positive, but their integral over the whole state space has to be equal to 1. So this integral equal to 1 is exactly the normalization. It exactly corresponds to the normalization that we have in quantum theory, that the trace of the density matrix is equal to 1. Here, the integral is somehow generalizes the trace. And then, given this, one can easily say, okay, so how do we measure probabilities of observing particle having some position or having some momentum? Well, this is quite easy, because what we will do is that we will assume that if we integrate one of the coordinates away, so if we integrate the state over position or over momentum, that we get a probability distribution. And hence we will assume that this is how we will measure probabilities of observing some position or some momentum. Here, the tilde q is the random variable corresponding to the position q. And in the same way, one can write down the formula for tilde p, which would be the random variable for the momentum. So this is nice. And in this way, we can actually measure positions and momentums and their probabilities. So far, it looks like a reasonable physical theory. Now, the energy. So we will measure energy using the Hamiltonian, because, well, that's how we do it in physics. And we will assume that the mean value of energy will be computed simply by integrating the Hamiltonian against the state. So this is a lot of assumptions, but well, as you will shortly see there, I'm not pulling this out of my hat, but this is quite well motivated coming from quantum and classical theory. But for now, please take this as given. So having these two things, we can have states, we can compute probabilities of observing position and momentum, and we can compute mean value of energy. But actually, this is not enough, because to have a meaningful theory with meaningful predictions, it's not enough to have mean value of energy, but we also need to be able to compute the probabilities of observing energy from some interval. Because if you know that mean value of energy is, for example, minus 0.5 electron volts, this doesn't tell you if you have a pure state or you have a mixed state. We need to have the probabilities, not only the mean values. And so this is now the big problem ahead, that to have a somehow meaningful physical theory, we need to get these probabilities of observing energy from some interval. But before I tell you how to solve this problem, I'll show you that actually this formalism also applies to classical and quantum theory, so that it's somehow grounded in reality. Because one of the very important aspects of GPTs is that classical and quantum theory are in fact in the class of GPTs. And so GPTs are generalizations of classical and quantum theory and not some hypothetical mathematical stuff. And so in classical mechanics, it's quite easy to see that this formalism applies, because all you need to do is that you need to formulate classical mechanics using the Hamiltonians, and then you have a phase space. And then instead of saying that your particle is at point as Q and P, you just say that it's described by some Dirac delta distribution, or in general some probability distribution, and you get exactly the same thing I described here, except for this description is a little bit more complicated for what we need in classical mechanics. But in quantum mechanics, we can get the same thing using Wigner functions. So these are the Wigner functions. And don't be afraid about the formulas. We don't really need them. It's just, if you've seen them, you know what they are. If not, it doesn't matter. Because the first one, this AW, is a Wigner function corresponding to observable A. And the second one, rho W, is a Wigner function corresponding to density matrix rho. As you can see, the only difference is there's a factor of 1 over H. And the interesting thing is that these functions are defined in such a way that if you want to compute the mean value of the observable A, you can just integrate the function AW against the function rho W. And you can also show that all of the other normalization conditions hold for the state. So in fact, what I introduced before as how to do GPTs in phase space, this also describes quantum theory using this Wigner function formalism. And it's important to remember that for spinless particles, these Wigner functions, they are completely equivalent to using wave functions. But the good thing is that we can also generalize these Wigner functions to other GPTs where we don't have the Hilbert space and when we don't have the wave functions. So now back to the problem, how to measure the probabilities of observing energy from some interval. So, I mean, before I finally tell you how to do this, let me tell you how to not do this, because there are two naive solutions that one can easily come up with, and they are not very good and they don't work. The first one is that essentially knowing the probability distribution of energy is the same as knowing the higher moments of energy. And so one can say like, okay, if I want to compute the expectation value of nth power of energy, then I just integrate the nth power of the Hamiltonian against the state. But well, this wouldn't work and this wouldn't pass because this is actually not true in quantum theory. And one can see that in quantum theory, this formula with the mean value and integral over power of Hamiltonian does not hold. That's because in quantum theory, in the Wigner description, we have to use the Moyal product of functions, not the standard function product of functions. As a matter of fact, one can also show that if this if we would postulate these things with the higher moments, classical theory is the only theory that satisfies this. So under some assumptions. So this would not be a very good way how to solve the problem. The second one is that, okay, maybe we know how to compute probabilities of position and momentum. So let's just treat energy as an independent variable. But this is not very good because, as we all know, energy is not an independent variable. Energy is a function of position and momentum. So we somehow deemed this approach unphysical. And so the approach that actually works is what we call the phase-based spectral measures. And this is literally just the replacement for the spectral measure of operator. Because as I told you before here, that for every observable A, you can compute this Wigner function AW and get all of the mean values from the function AW. In the same sense, you can compute the Wigner function corresponding to the spectral measure of the observable A, and you can use that. And this is exactly what the phase-based spectral measure is. It's just a set of functions that have some, and there are some normalization rules for these functions, and these functions exactly generalize the spectral measure of operator, except for there is no Hilbert space and everything is in phase space. So let me show you an example. Let me show you the harmonic oscillator. This is the example that we have, a toy model of harmonic oscillator. And now it can appear that there's a lot of things, but this really describes almost everything there is. So we see here several functions plotted as functions of a variable r. This variable r is essentially just p squared plus q squared. So this is just the energy in the phase space. And it's also sprinkled with some other constants so that it all works out. But it's essentially just p squared plus q squared. This blue function that you see now, this is the phase-based spectral measure. This is the function of the phase-based spectral measure corresponding to energy equals 0. So if we would integrate this function against the state, we would get the probability of observing energy equal to 0. So as you can already see, this toy model of the harmonic oscillator has ground state energy equal to 0, not h bar omega divided by 2 as it is in quantum theory. The next function, this orange one, is the phase-based projector corresponding to the first excited state, which is now h bar omega half. So if you would integrate this against the pseudo probability density, you would get the probability of observing the energy h bar omega divided by 2. And then there's this green function, which is the next phase-based projector corresponding to energy h bar omega. And now we can go to states. So this brown function that you see with the shading, this is actually a Wigner function of a state. So this function gives us a state, which, as you can see, has a negative Wigner function, which already hints at some non-classicality of the state. And moreover, one can see that this is an eigenstate of the harmonic oscillator. So even in this toy model, such things exist as a state with negative Wigner functions. This other one has positive Wigner function, and so one would assume that it's classical, but this is not true. because since we since we have some different phase space spectral measure of energy, we changed the way how we measure energy. And so we also changed the meaning of positivity of state. So even though this state has positive Wigner function, it's not classical. And actually, one can show that this purple state, it exhibits what we call tunneling properties, which basically means that this state is more spread out in position that one would somehow assume it could be based on classical concepts of conservation of energy. So this just means that the state is somehow pushing against the potential bit more than one would assume should be possible if conservation of energy would be applied in a very classical sense. This does not mean that energy is not conserved. It is. It just means that it's not so straightforward to apply it, and one should be very careful about how it is applied. And this is exactly what we call tunneling properties. And so this is the toy model of the harmonic oscillator. Of course, it's not the only thing that one can construct. One can change the phase space spectral measure to construct different toy models of the harmonic oscillator, and one can also construct different theories. And there's also more to be discussed, for example, time evolution or maybe other observables that one can get. But if you are interested in this, the paper is on the archive and hopefully soon to be published. So you can read more there. And with this, I'd like to thank you all for the attention. And if you have any questions, please go ahead and ask.
Thank you very much, Martin. Perfect time. Thomas has a question. Please go ahead, Thomas. Tom.
Thanks. Yeah, so that was a very interesting talk, and I think it's very important task to try and bring space-time back into GPTs. I had a question that wasn't clear to me. If you take your construction but do it on finite dimensional phase spaces, you just get the standard GPTs. Like, can any finite dimensional GPT be understood as using this kind of pseudo densities on some finite dimensional state space?
Yes, yes, of course, one can do this.
Okay. Yes, thanks.
Thank you. We have another question. TZ Prop.
Hi, sorry, I forgot. It's Sula Prop.
Okay, sorry.
I forgot I'm calling in from my phone, so it doesn't have my full name.
Okay.
So this is fantastic. Thank you. I'm curious about in the GPTs. You've managed to define a Wigner function. Do you still have things like the Fokker-Planck equations where you can evolve the Wigner function directly, or do you have to evolve the density, or the GPT equivalent of the density matrix and then get a Wigner function?
So in the toy model, the Wigner function is the GPT equivalent of the density matrix. And yes, we actually, in the case of harmonic oscillator, we just say that the time evolution is given by the Liouville equation. So this is the same as in quantum and in classical and quantum theory. So there is this time evolution.
Great, thank you. It's the exact same equation. Cool.
Yeah, I mean, okay, so one can then argue that this only holds in quantum theory for the harmonic oscillator. So what about other potentials? And for that, that's up to, that's an open question, that how to generalize the time evolution for other potentials and how to get something meaningful. And we're working on it.
Nice. Any other question for Martin? Doesn't seem to be the case. So thanks again. I think we can now move on to the final contributor talk before the panel session. So this is, okay, perfect. David Schmidt from the University of Gdansk. This is again about causal inferential theories. Okay, the title is a bit different from the website, but it's simplified. So please, yeah, go ahead.